In this video, we're going to take a look at how to find the equation of a parabola when you're just given the graph. So we're going to work through three examples here. Let's dive right in. In our first example here, the first thing we want to think about is what form of the equation is going to be easiest to use for a given situation here. So we can see our x-axis is here, our y-axis is here. We can see that we know the vertex, so that's helpful. And we also know the x-intercepts. For this specific example, I'm going to work through focusing on the x-intercepts. You could also answer this question by focusing on the vertex, but I wanted to start with factored form first. So, I know in general, factored form for a quadratic equation is going to look like this. Y equals a, x minus r, x minus s. Hopefully you recall that r and s are our x-intercept values. So let's go back to our graph and let's identify those clearly. So I'm going to have one x-intercept here. X is 3, y is 0. I'm going to have my other x-intercept over here. X is negative 5, y is 0. And that means our r and our s values are going to be negative 5 and 3. And remember, we have to flip the sign. So we're going to end up with, my equation is going to look like this. Y equals a, x minus negative 5, x minus 3. And then we don't like to have the double minus and stuff, so we'll tidy it up a little bit. Y equals a, x plus 5, x minus 3. So we're already almost done. We have most of the equation. The only thing we still need to figure out is the a value. Now hopefully you remember that the a value is related to the step pattern. So what we can do is, let's remember in general, our step pattern is always going to follow this pattern. A times 1, 3, 5, and so on. Let's take a look at our graph. Let's see what our step pattern is for this specific parabola, and then we'll do some calculations and find our a value. To find our step pattern, we want to start at the vertex. And remember, we're going to go over 1 to the right, and then see how far up we have to go. One thing to watch out for, and I know I've seen a few of us make this mistake previously, take a look at your y-axis. Make sure you're going over one full unit. In recent days, I've seen some people, they went over like one square on the graph and then tried to go up. Don't go by the squares or on the graph or your grid. Go by the actual one unit as marked on your x-axis or y-axis. So let's take a look. We're going to start at our vertex, and I'll actually keep this tidy. I'll use one of these tools. Let's see if we can do this. So we're going to start at the vertex, and we're going to go, oops, wrong shape. We're going to start at the vertex, and we're going to go over 1, and then we're going to go up. The question is, how far did we go up by? Well, let's check our squares here. From here to here is 10. We have 1, 2, 3, 4, 5 squares. So every one of these squares represents 2 units. Which means if I went up 1.5 squares here, I went up 3 units. So I went over 1, I went up 3. Let's try that again. Next step, we're going to go over 1. We're going to go up by, we're going to have to count here. So each square is 2. 2, 4, 6, 8.5 is 9. So over 1 again, up 9. Let's do the next step. We have enough information already to stop and calculate, but might as well do at least 3 steps in our step pattern to make sure we can clearly see the pattern. So once again, we're going over 1. We're going to go up by, let's count. Remember, each square is 2, 2, 4, 6, 8, 10, 12, 14.5 is 15. Which means our step pattern is going to be 3, 9, 15, and so on. You can probably already figure out what the a value is in your head, but let's do an actual calculation. I'm basically saying that a times 1 is equal to 3. So let's write that out as an actual equation. A times 1, or 1a, is equal to 3. And if we divide both sides by 1, or we can just see pretty straight away that a is equal to 3. Let's do a couple extra calculations just to confirm. A times the second step of 3 is going to equal 9. So let's take a look. A times 3, or 3a, is equal to 9. Divide each side by 3, we see that a is equal to 3. So far so good. Let's still do our final calculation just to make sure this holds true. A times 5 is equal to 15. So 5a equals 15. Divide both sides by 5. A equals 3. So we've done more than enough work here to prove that a is equal to 3. So we can just finish writing out our equation. Y equals 3, x plus 5, x minus 3. And if you're working at home and want to verify either this answer right away, or if you're doing homework and want to verify, Desmos is your friend. Just head on over to Desmos, either on the website or using the app on your phone or other device. And you can quickly double check, plug in the equation, and make sure that it looks like the graph you're trying to match. I'm not going to bother doing that. I want to keep this video as concise as possible, but that is something you can easily do if you wish. Let's take a look at our second example, and this time I want to practice using vertex form. It honestly doesn't matter which form you use, as long as you have an easily read vertex and or an easily read x-intercepts. If for some reason the x-intercepts were like kind of in between and you really couldn't tell the exact values, then they would not be a good way to solve this problem. Basically, if only the vertex is really easy to see, you should use the vertex. If you can only easily see the x-intercept because the vertex is some weird decimal or fraction value, then don't use that. Just use the values that are most easily read. And if you can read both of them easily, then it's really up to you, or it's up to what the question is asking you to do. So if the question says you have to use vertex form, then obviously you should use vertex form. So we're going to use vertex form for this one. Let's take a look. So I see my x-axis here, y-axis here, and my vertex is going to be right here. So the values are going to be x is 1, y is -2. Let's remind ourselves what the general equation looks like. And anytime you're working through one of these questions, it's always a good idea to start with the general equation. In fact, I'm specifically going to look for that when you're doing a test or an assignment. So you should always start off your questions this way. And just in general, you should always be trying to do things the way I do them on the board. There's a reason I model the correct way to answer questions. Don't just decide that the work I show is unnecessary and skip it, because seeing your process is the best or the most important thing on your assessments. I want to see that you understand the process. I don't care so much if you get the correct final answer. I care that you know how to do the steps in between. So make sure you're showing your work. Make sure you're keeping things tidy. Make sure I can follow the flow of your work. Some of you work like this, like you work down and then around and then back, and then your final answer is here. Please don't do that. Try to work like straight down the page. If you run out of room and need to move over, then you can go and keep doing your next line here and next line here, and then have your answer at the end. Just try to keep it really clear and easy to read. That is something I will mark you on, and if I can't read it, it's wrong. Anyway, back to this specific question. We're taking a look at our vertex form of the quadratic equation. Y equals a bracket x minus h squared plus k. Hopefully you remember that h comma k is the coordinates of our vertex. And look, we already know the h and the k, so y equals a x minus 1 squared plus k. K is -2. We don't like switch the sign or whatever. It's just going to be -2. So far so good, but we still have to find our a value. Just like before, remember, our step pattern is always a times 1, 3, 5. Let's zoom in on our graph and let's find our step pattern on this graph. So we're going to start at our vertex. We're going to go over 1, and we're going to go up. We're going to go up by 1 square in this case. Let's see how big 1 square represents. So this is a distance of 2. This is a distance of 1. So each square represents half. So in our specific situation here, we went over 1 unit, and we went up by 1 square. We said each square is a half, so over 1, up half. So my actual step pattern here starts with half, You can probably figure out your a value already, but I want to go through a few steps so we can prove to ourselves that it's consistent. Once again, for our step pattern, we're going to go over 1 and up until we hit the graph, or hit our curve. So we went over 1, and we went up by 1 square, 2 squares, 3 squares. Each square was half, so we went up by 3 halves. And let's do this one more time. So 3 halves is 1.5. Well, I'll leave it as an improper fraction, 3 halves. If you want to think of it as 1.5 or 1.5, that's fine. Doesn't matter which way of representation you want to use right now. For our next step, we're once again going to go over 1, and we'll go up until we hit our curve. So we're going to go up. And let's count how many squares that was. Each square is a half. So half, 1 half, or sorry, 1 half, 2 half, 3 half, 4 half, 5 half, 5 halves, or 2.5, or 2.5. I'm going to leave it as 5 halves because I think that's easiest to work with right now. I'm not going to do 3 calculations this time, but I am still going to use 1. We're going to notice here that 1 times a, or a times 1 equals half. So 1 times a equals half. A equals half. You can repeat the calculation again like we did in the previous example to prove to yourself and make sure you understand. But I'm going to go straight to the answer. We're going to say that y equals half x minus 1 squared minus 2. Once again, if you want to check with Desmos really quick, you can toss our equation in there and make sure that the graph that is produced is the same as the graph you're seeing on the screen here. In our final example here, we once again have the choice of using either the vertex form or the factored form. I'm going to choose to use factored form just so I can kind of switch back and forth for examples and show you both, but it's really up to you. So I'm choosing to focus on the x-intercepts, so I'm going to start by labeling them. This x-intercept here is at x is 1, y is 0, and x is negative 1, y is 0. I don't need to worry about the vertex right now because I'm focusing on factored form, so I'm not going to bother labeling it, but you could if you wanted to. I'm going to start out with the general form of the equation. Y equals a, x minus r, x minus s. And we already found our r and s values, so x plus 1, x minus 1. If you switch it around, if you just change which ones are r and s, it really doesn't matter. So if you work this way, x minus 1, x plus 1, that's still going to give you the exact same equation. That's totally fine. Because you're just multiplying these. So like imagine we had 2 times 3, or we had 3 times 2. They both equal 6. So when we're multiplying things, the order does not matter. That's called the commutative property, where order doesn't matter. Anyway, I'm going to focus on this one. Just know that if you decide to write it this way, that's totally fine. So I already know all my values in my equation. X and y represent a family of numbers. Don't need to change them. I do need to figure out the a value. Once again, we're going to look at our graph and find our step pattern. And after we do that, I will show you an alternate method, which some of us had a chance to see in class last week already. So we're going to start with our vertex. Remember, we're not going over one square or one box or one grid line. We're going over one unit. So 0 to 1 is here. So I'm going to have to go over 2 squares. So starting at the vertex, we're going over 1. And notice this time, instead of going up, we are going down. That should tell us something about our a value, and we'll talk about that in a moment. So I'm going to go down, and let's confirm how big these squares are. So let's see, this is 0 to 5, 1, 2, 3, 4, 5. That means each square represents 1 unit. So in this case, we have gone over 1 and down 1. So I'm going to use a negative 1 to represent the down. Let's find our next step. I'm going to go over 1 unit to the right, and I'm going to go down until I hit my graph, my curve again. Oops. So we went over 1, and we went down 1, 2, 3, 4, 5, 6. So we're going to use negative to indicate that we are going down. Let's find one more step. Some of you may have noticed technically we could just do one step and find the a value, but it's just like finding first differences. It's advisable to do some extra steps just in case you make a mistake. So always have a little bit of extra backup information to help with your calculation. Make sure you didn't accidentally count the grid lines instead of the units, that kind of thing. So we went over 1 and we went down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So negative 10. All right, let's write out our step pattern. Remember, it's always going to be a times 1, 3, 5, and so on. In our specific case, we found that our steps were negative 1, negative 6, and negative 10. And you might notice that we have a problem here, and this is why it's good to do more than one step for your calculation. I made a mistake here. When we went down on our first step, we said each box represents 1 unit. I said we went down 1, and I wrote a negative 1. That's incorrect. We went down by 2. So this should be negative 2. And the first step here in my step pattern should be negative 2. That was a real mistake. I didn't do that on purpose for the video, but that is why I measure the steps more than one step in case I make a mistake, because it's obvious from the pattern here that it wasn't 1, 6, 10. It had to be 2, 6, 10. Let's quickly calculate our a value. Once again, it doesn't matter which set of info you use here. You could use a times 1 is negative 2. You could use 5a is negative 10. You're going to get the same a value however you calculate it, but let's do the easy one. 1 times a is negative 2, therefore a is negative 2. We can write out our answer, y equals negative 2, x plus 1, x minus 1. The thing that's different about this example, the most important thing to notice, is that our a value was negative. That's how this is different from our previous questions. We have discussed previously as well that when a is negative, our parabola is concave down, so it has the frowny shape. So when you're finding a step pattern for a graph that's opening downward, make sure your a value is negative. Let's say as you went through your step pattern, you forgot to write the negative sign. You just used positive 2, positive 6, positive 10, and then you calculated and got an a value of positive 2. You should know right away that's not possible. This graph opens down, and that's a sign that you should flip the sign or make it negative, or go back all the way and double check your calculations to make sure you're good. If you understand everything up to here, then you're good to go. I'm still going to show one more method though, just for those who are interested. I'm going to move this to the side to give me a little more space. And some of us saw this in class yesterday, or some of us saw this in class last week. We have used a similar method when we worked with linear equations and stuff. But let's just see another way to do this without finding the step pattern. So we still start with the general equation. We wrote out our general equation, just missing the y value. So I'm going to keep working from there. Y equals a, x plus 1, x minus 1. And this time, instead of going to our graph and counting our step pattern, we are going to sub in a known value from the curve. So I can choose any point on the curve that I know. In most cases, so it's going to be easiest to use the vertex. So the vertex is just some point on the curve where I know the values. And I know that here x is equal to 0 and y is equal to 2. What I'm going to do is I'm going to substitute that point into my equation and calculate my a value. So I'm going to sub in point. In this case, I'm going to sub in the vertex, which had the coordinates of 0 and 2. So write out the equation. Instead of y, x1, y1. Instead of y, I'm going to sub in a specific y value. Don't know my a value yet. Instead of x, I'm going to sub in my specific x value. 0 minus 1. And make sure you actually calculate this. Sometimes people will take a shortcut. They'll say, oh, I got zeros. I'm multiplying by 0. All that stuff just goes away. Not quite. Be careful with that. Let's actually calculate. 2 equals a. 0 plus 1 is still 1. 0 minus 1 is still negative 1. Now we can calculate. So 2 equals a. 1 times negative 1 is negative 1. 2 equals a times negative 1 is negative a. And basically I need to get rid of the negative, or I want to get a by itself, not negative a. I can just flip the signs on both sides of the equation. That's allowed. Or you can think about it as dividing each side by negative 1. Either way, we're going to end up with negative 2 equals a. And hey, that's the same value we had over here using our step pattern method. So I can just state that the equation is y equals negative 2, x plus 1, x minus 1. So this final example here is just to show you that we can use the step pattern to find our a value and therefore find the equation of our parabola. Or we can also use substitution like we have in the past, plug in a known point from the equation and find our missing value, which in this case is the a value. One other thing you might have noticed is that we did some work with the factored form of the quadratic equation. We did some work with the vertex form of our equation, but we didn't do any questions involving the standard form, y equals ax squared plus bx plus c. This one is a little less intuitive to work with, and there is a way to find it from the graph. Specifically, we're going to find factored or vertex form and then convert it into standard form, but we're going to talk about that in Quadratics Part 2, so that's not something you need to worry about quite yet. Instead, we'll see that in our next unit.